In this video, we're going to be talking about chemical reactions and chemical equations. A chemical change, also known as a chemical reaction, is a change in which the chemical identity of a substance is changed. We talked about physical changes, and that was a change in which we could see that something had occurred, but that the chemical identity of the substance remained the same, such as with boiling. A chemical change, we actually see that the formulas of the reactant, of what's known as the reactants, the starting substances, is different than the formulas for the ending substances known as products. There are a number of ways in which we can tell if a reaction has occurred. Now, these are all good indications that a chemical reaction has occurred, but none of them are guarantees. So we have to use other clues that we know about the reaction as well. So if, say, you add two substances together and we see one of these things happen, that's a good indication that a chemical reaction has occurred. But I'll give some examples of when that may not necessarily guarantee it. So these changes that we can look for are a color change, a smell change, a bubbling or formation of a gas, the formation of a solid, also known as a precipitate, a temperature change, which you can feel if we were to do the lab that we were planning on doing as part of our normal curriculum, you would have been feeling the outside of a test tube with your hand. And then also light given off, or if you see fire, that's another indication that a chemical reaction has occurred. So for some of these, I wanted to show you examples of what these would look like. And so the next few slides are just going to show us some examples of chemical reactions. So when we see a color change, such as in this video, this is a really dramatic chemical reaction, series of chemical reactions known as an iodine clock reaction. And this is a series of reactions that happen at a very consistent time interval. And we see that one of the products is a black color, whereas another product is this clear, kind of yellowish color. And when that color change is occurring, that's a sign that a chemical reaction has occurred. Here's an example of bubbling or gas formation, and this is a reaction you can do at home. It's simply adding vinegar and baking soda together. The formation of a solid or precipitate is another indication. Here we see that we have two clear liquids that are being added together. And when they mix, a bright yellow powder is formed, and that eventually settles to the bottom as a solid or precipitate. This is an interesting reaction that occurs when you react steel wool, which is pure iron, and it can react with oxygen when it is lit on fire. And the reaction can get pretty bright, like we see there, when the reaction is in the presence of a more pure oxygen gas rather than air. So we see sparking happening, light, heat given off. These are all really good indications that a chemical reaction has occurred. So how we can describe these chemical reactions is through writing what's known as a chemical reaction equation. We write the formulas of the reactants on the left and the formulas of the products on the right, and we separate those two using an arrow. Plus signs are used if we have multiple reactants and products rather than commas. And oftentimes you will see symbols written after the formulas of each of the substances to indicate physical states. The four common parentheses symbols are given here. We can use S to indicate a solid, L to indicate a liquid, G for gas, and AQ for aqueous. This is what we use when we dissolve something in water. Now, liquid and aqueous are often confused for each other. We use liquid when we have a pure substance that is in liquid form. And if we have something dissolved in water, remember that that is a solution. or a homogeneous mixture. So if it's dissolved in water, homogeneous mixture. Before we get to writing chemical equations, I would like to do a quick review of how we can count atoms when we see them in a chemical formula. So numbers can appear in a couple places in a chemical formula, and I wanted to differentiate between them. When we see a number as a small number at the end, this is known as a subscript. So Cl2 with the subscript 2, that means that those atoms are bonded together in a single chemical formula. When we see a 2 at the beginning with a big number, this is called a coefficient. This means that they are not bonded. But we still count 2. So both of these examples have 2 atoms of chlorine, 1, 2, 1, 2. But the difference between the two is when it's a subscript, those 2 atoms are bonded. When it is a coefficient, they are not bonded. Now you could have both a coefficient and a subscript, and in that case, when we're counting the total number of atoms of chlorine, we're actually going to multiply them together. We have 2 chlorine atoms per chlorine molecule, so this is referred to as a molecule. And when we add them all together, 1, 2, 3, 4, we multiply the subscript by the coefficient for a total of 4 atoms in 2Cl2, 2 atoms of chlorine. So that is a skill that we're going to be using when we write our chemical equations. We can also see that some molecules may have parentheses to indicate numbers of atoms. So for example, if we see this formula here, this is called calcium hydroxide. And if we were to draw a picture of that, we would see that the OH is a unit. And this subscript means that I have 2 of these units. So 1 OH here and 1 here. So when we count our numbers of atoms when we have parentheses, that 2 is for all of the elements within the parentheses. So here I have 1 calcium atom, 2 oxygen atoms, and 2 hydrogen atoms. Let's give this example a try together. How many oxygen atoms are in the following? I would like you to pause this video and give this a try for each of the 3 formulas. Then when you're ready to see the answers, press play again. In in sodium hydroxide, oh my, sodium hydroxide, the first compound here, NaOH, we have 1 oxygen. When there is no subscript after the element symbol, that means there's just 1. In our next substance, called aluminum hydroxide, we have a 3 on the outside of the parentheses. That indicates we have 3 oxygen atoms. In our third substance, known as calcium hydroxide, we actually have 2 numbers that we have to deal with. The subscript 2 refers to 2 oxygens, but then we have 3 of the entire thing. So we're going to multiply 2 times 3 for a total of 6 oxygen atoms. When we are writing our chemical equations, we need to keep in mind a very important law of nature, and that is called the law of conservation of mass. What this says is that in a chemical reaction, you never have atoms created nor destroyed. So if I have a chemical equation written, I have to have all of the atoms accounted for on both sides. The reason for this is because in a chemical reaction, what's happening is that the atoms are simply rearranging themselves and breaking existing bonds and forming new bonds. The atoms themselves are still present in the reactants and the products. And the numbers of each type of atom is the same in both the reactants and the products. So our chemical equations that we write have to reflect this. And they reflect this by doing something known as balancing equations. We must ensure that our chemical equations are balanced. And what that means is that all of the atoms of each type of element have the same numbers represented in both the reactants as well as the products. So balancing equations is actually quite simple when we look at the rules. Essentially, there's one rule. The only thing we can do when we balance equations is that we can place coefficients, so those are the big numbers, in front of the chemical formulas to reach equal numbers of each type of atom on both sides of the equation. When there is no coefficient, that means that we have just one of that substance. For me, I am okay with leaving it blank or putting a 1. There are a number of things that we are not allowed to do. So number 1, that is the only thing we're allowed to do. We are allowed to place coefficients. We're not allowed to do anything else. So you can't change a chemical formula, you can't take away or add subscripts within a formula, and you can't take away reactants or products. All of these things, if you attempted to do that, would then change the meaning of the chemical reaction itself. And so it would no longer represent the reaction you are trying to write. Once you have balanced your chemical equation, take a look at all of your coefficients and make sure that they can't be simplified, much like a fraction. So if they're all divisible by 2 or 3, you want to simplify them if possible. So I want to show you some examples, and I want to show you how I go about balancing equations. If you have balanced equations before and you have your own system, you can use whatever system you prefer. Myself, what I like to do is directly underneath the arrow, I like to list out all of the different elements in that chemical reaction. So this reaction we show here is breaking down water into its component elements. So we have H2O breaking down into oxygen gas and hydrogen gas. Now oxygen gas and hydrogen gas, they are what's known as diatomic elements. Diatomic elements, when they exist as an element, have 2 atoms bonded together. So H2 would be 2 hydrogen atoms bonded together. Oxygen is also a diatomic element. So what I do is underneath my arrow, I list all of the elements that are represented in that chemical reaction. Then I count up how many of each type of atom are on each side. So on the left side of the reaction, we have the reactants. In H2O, there are 2 atoms of hydrogen and 1 atom of oxygen. In the products, I'm going to do a separate count. I have 2 atoms of oxygen and 2 atoms of hydrogen. Our goal is for each element to have the same number on both sides of the equation. Right now, our hydrogens have the same number on both sides, so we would say that hydrogen is balanced. But oxygen is not balanced. There's only 1 oxygen on the left side and 2 on the right side. So we need to add coefficients so that those numbers are equal. And that is really the only thing you can do. These blanks right here, you can put a big number in that blank, and that's the only thing you can do to balance an equation. So to balance this, we're going to need more oxygens on this side. So we're going to add a coefficient in front of H2O. Now my goal would ideally be to get that to be equal to the other side. So if I wanted to have 2 oxygens, I need to have 2 waters. So I first write a coefficient, and now I'm going to reflect how that coefficient changes the number of hydrogens and oxygens. So I'm going to cross out my hydrogen and oxygen. Always put a coefficient first, cross out the counts of those elements that are affected by that coefficient, and recount. Now, this does change my hydrogen, and that is okay. That's part of the process. So now I have 2 times 2, 4 hydrogens on the left side, and 2 times 1, 2 oxygens. So in effect, I balanced the oxygen atoms, but now my hydrogen atoms are not balanced. And that's a totally normal part of balancing chemical reactions. So now that our oxygens are balanced, we're going to go back to our hydrogens. And we need to now add more atoms of hydrogen to the right side, the product side. Now there's only one product that contains hydrogen, the H2. And I need to get those numbers to match. So in order to get 4 on this side total, I'm going to put a 2 in front of H2. That changes my count to 4. And now that I see that hydrogen is 4 and 4, oxygen is 2 and 2, so I have a balanced reaction. Now in front of this oxygen, notice nothing is there. That is how I would normally leave it. If you want to put a 1, you sure can. And this is our balanced reaction. Why don't you give this reaction a try? So pause the video and try balancing this reaction, and then we'll go through the solution together. So I'm going to, underneath my arrow, list out all of the elements that are involved in this chemical reaction. We have copper, oxygen, hydrogen, and chlorine. I'm going to count how many of each type of atom I have on both sides. I have 1 copper, 1 oxygen, 1 hydrogen, and 1 chlorine on the left or reactant side. And on the product side, or the right side, I have 1 copper, 2 chlorines, 2 hydrogens, and 1 oxygen. So my copper and my oxygen are balanced, but my hydrogen and chlorine are not. I often just pick an element to balance out first. It really doesn't matter which one you start, so I often just go with the order that I have written. So if I want my hydrogen to be balanced, I need more on the left or the reactant side. So I find the compound that has hydrogen, HCl, and I'm going to add a number in front of it that's going to make my 2 hydrogen numbers match. So if I put a 2 here, that's going to change my count. So I always put a number in front of the formula first, and then I cross out the counts for all of the elements that are in that formula, and I recount. So I have 2 hydrogens now, and I have 2 chlorines. So that means that when I balanced my hydrogens, I also balanced my chlorines, and this is the only coefficient that I need to balance this chemical reaction. Here's another one. Give this one a try. Pause the video, and then we'll go over it together. So once again, I'm going to start out by listing all of my elements involved in this chemical reaction underneath the arrow. I like to draw lines around it, and then I do my counts. I have 1 silicon, 2 oxygen, and 1 carbon on the left side. I have 1 silicon and 2 carbons. So this is an example where we have carbon existing in 2 different products, and that is very common, and 1 oxygen. So I have a balanced silicon, and my oxygens and my carbons are not balanced. I'm just going to take it one element at a time. So to balance my oxygens, I need more oxygen on the right. I see that oxygen is only in my CO gas, so I'm going to put a 2 here, and that's going to affect both my oxygen and my carbon counts. So I am going to recount. So now I have 2 oxygens, and I have 2 carbons, but don't forget the carbon in the other product. So I have 3 carbons. So now my silicon is balanced, my oxygen is balanced, and to balance out my carbon, I need more carbon on my left side. Luckily, carbon's all by itself, so if I need 3, I can put a 3 here, and that will balance out my carbons. Let's try one more example together. This one is actually a trickier one. And so I will give you the hint if we list out our 3 elements involved here. This is a more challenging one. If you balance your oxygen last, so leave oxygen last, that will actually make your life a little easier. So why don't you try balancing this carbon first, then hydrogen, and finally oxygen, and then we'll talk. So when I'm counting up my different atoms, I see that I have 4 carbon on the left side, 8 hydrogen, and 2 oxygen. On the right, or the product side, I have 1 carbon. I have 2 oxygen plus 1 oxygen, so that gives me a total of 3 oxygen. And my hydrogen, I have 2. So like I said, I recommended balancing oxygen last. So I'm going to start with my carbon. I usually just like to start with whatever is listed first. There's really no trick to it. And if I want 4 carbons on the right side, I need to find the substance that has carbon and decide how many of those total molecules will get me to 4 carbon, and that is 4 carbon dioxide. So that's going to affect both carbon and oxygen, so I cross those 2 out. I now have 4 carbon, and in the oxygen I have 4 times 2, that's 8, plus this one over here. So I have 9 oxygen, and I'll just cross those out. Now let's balance our hydrogen. I have 8 on the left side, and they come in packages H2O. That means that hydrogen is always going to come in packages of 2. So what number times 2 will get us to 8? That is a 4. So that number 4 will affect both my H's and my O's. So I'm going to cross out my H's and my O's. I now have 8, 4 times 2 hydrogen, and now I have 4 oxygen, and here I have 4 times 2 oxygen. 8 plus 4 is 12 oxygen total on the right. So now I can balance my oxygen, because notice that oxygen on the left is only by itself in packages of 2. How many of those O2s would I need to equal out the 12 on the right side? I would need 6. 6 times 2 is 12. And this is my balanced chemical reaction. So in your assignment for this folder, you will be practicing doing some more balanced equations. If you're still feeling a little overwhelmed with this, I do recommend Googling what's known as PHET balancing. That's going to give you a website with some more practice and a program where you can look at the consequences of adding these coefficients. You can actually look at pictures of the molecules. So that might be a more accessible way for some of you to see how to balance these equations.